Hey, what's up, guys? This is Chung here. So let's take a look at last problem of this week's weekly contest, number 1665, minimum initial energy to finish tasks. So you're given like an array of tasks, and each task has like this actual and minimum value, where the actual is the actual amount of energy you need to spend for this task, and the minimum is the one that you require to begin with this task. Right, so here's some examples here. For example, if the task is 10 and 12, you need to have at least 12 energy to begin with. And after this task, you will have 2 energies left. Right, so basically, so this is the energies you will be saving right after completing this task. But first, you need to at least have this task, this number of energies to begin with. And you can finish this task in any order you like, and then you need to return the minimum initial amount of energy you need to finish all the tasks. So every time you guys see like this minimum, there should be some like options in your mind. So the first one is like the BFS. Of course, this one is not the BFS problem. And then the second one will be what? The DP, right? DP can always give you can give you the minimum or maximum values. But for this problem, the issue is that, all we have is like a unsorted tasks here, and where you can take the task in any order. You don't even have a target, right? And that we need to use these things to get our target. And for the DP, yeah, so basically, I think if you want to use DP, probably you need to sort it first, right? And then as long as you sort it, and then you don't have to use DP. You can use like a much faster solution. In this case, it's going to be the greedy. The greedy one can also give you the correct answer. So if you watch closely, the tasks, let's say given like this kind of task. So in order to finish the current task, right, we need to have like the the energy to start with, right? Like I said, by completing some of the tasks here, you can save some energies. So our approach is like this. We want to save as many energy as possible so that we can use less energies. We can spend less energies to complete the following tasks, right? So basically, in order to save as many energies as possible, we need to process the task that can give us the most saved energy, which means that we need to sort by the second element, subtract the first element, and then we do a reverse sorting on that, so that we can just we can start processing the tasks can save us energies, the most energies, and then we will use those saved energies and try to process the next one, right? So basically, we're gonna have like for every time we're gonna have like saved energy, and we just need to for each time when we have like at the current task here, we'll check if the current saved energy can um, can start this task, right? If it cannot, then it means that we need those few more energies to start with, right? And then we'll just add those kind of energies into our answers, and then after that, you know, we can start this task. And after finishing this task, we'll also have like this 4 minus 2 energies to be saved, right? And then we just keep going until we reach the end, and that will be the final answer. And that's basically the greedy solutions here. I'll implement that actually. So besides the greedy solutions here, I'm also I'm also going to talk about the binary search solutions, which is also unlog solutions here. So, but let's try to do the greedy one first. So, like I said, I have to do I need to sort by the saved energy, which is going to be the key equals to lambda x equals to how to do this 1 minus x0, right? And since we're going to process from the end, I'm just going to do a reverse equals to true. Okay. And let's say we have a answer equals to 0, and here we have a current saved. Current saved equals to 0, right? So now let's try to process each of the tasks here. So we have a actual and we have a minimum, right? So we have actual and then we have a minimum, right? And I'll just use a, can I use M? I'll just use minimum, but actually minimum is a keyword. So yeah, I think it should be fine for in tasks, right? So first we check if the current minimum is greater than the saved, right? If it's greater than the saved, it means that we need a few more energies to start the current task, right? So how many energies we need? Like needed equals to m, the minimum, minus saved. Actually, so here I'll just spell these things out here, right? And that's that. And yeah, and our answer will be what we need to accumulate this needed energies we need here, right? Now, now the current saved, right? So the current saved will be increased, right, by this needed, and then after that, right, after that, so basically after this if statement here, now we can start current current task, right? So after finishing the current task here, the current saved will be the what? Will be the current saved minus the actual, right? So assuming we have a lot of saved energies, which can also cover the current minimum, right? So that we won't go into this if here, and all so which means that we will still be using the saved ones from the previous step. But after finishing this current step here, task here, we will also need to subtract the current cost or actual from the current save so that we can start the for loop, start the update the current saved energy and start for the next for loop here. And then in the end, we simply return the answer. That's gonna be the final answers we need. Okay. Line 3. Okay. All right. Submit. All right. So as you guys can see here, so the time complexity for this one is the to sort tasks here, we have a unlog n, right? Of unlog n. And here it's just a on here, right? So the total is on log n. So yeah, so that's the greedy solutions, right? And then actually there's like another interesting solution for this, which is the binary search. Because the binary search, for the binary search, we also need to these things. But the binary search idea is like this, since we want to search the answers directly. Now the question is that with given like a starting energies, can we finish all the tasks? That's gonna be our condition check for the binary search, right? And so for to check that, we also need to follow these sortings here because we want to, given like total energies, we uh, we still want to follow the same logic as the greedy one, which means that we want to finish the tasks that can give us more savings on energies, and then we'll just try to finish the task one by one, and then we'll see if we can finish all of them. So that's why for the binary search, we need a left and a right, right? So the left one is going to be the minimum values. So what's going to be the minimum value? So the minimum value will be the actual the sum of the actual cost, the actual sum of the actual energies we need, right? So that's why I'm going to have like a sum of the actual for actual and the minimum in tasks, right? So that's going to be the minimum, the starting point of the binary search. And how about the ending point? So the ending point is obviously the total of the minimum, right? That's going to be the that's going to be the total, the right, the maximum value we're searching for here. That's why I'm having two sum here, right? To get the left and right. And then now let's just write the template, right? Basically, while the left is smaller than right, right? And then we have a middle because the left plus right minus left divided by 2, right? And then if helper, so I'm going to just call it helper, if the middle one is true, which means that if we can finish all the tasks, then we'll try to set either the left or right pointer. So in this case, since we're getting the minimum values, which means that we will need to set the right equals to the middle, right? And then left, else left equals the middle plus 1, okay? And then in the end, we simply return the left. Since we're doing a left equals to middle plus 1, we don't have to do a plus 1 here. So now let's implement that helper functions here, right? So the helper functions means that given like this middle start energies, can we finish all the tasks? And so let's try to finish the tasks one by one. So we have a actual and we have a minimum, right? In the tasks, right? Basically, if the middle is smaller than the m, right? Then we know we need to return false, which means that the middle is not enough to start the current task. That's why we're going to return the false. Else, we just do a middle. We just subtract this the actual from the middle, right? And then in the end, we return true, which means that we can, with this middle given starting energies, we can complete all the tasks, right? And then in the end, we return the left, which will be the answer we're looking for here. Run, submit. All right, so it also passed. But as you guys can see, so this one is a little bit slower. So the reason being is that, even though the total time complexity for this one is also n log n, because here we have n log n. So the helper functions here, so it's a O of n, right? And for the binary search is a log n. So in total, it's still a n log n. But we have like two n log n here, comparing with the other one, which is the n log n plus on, right? Here we have a n log n plus n log n, and that's why This one is a bit smaller, but I mean, this is like also a good practice for the binary search. I mean, yeah, I think either way is fine. I mean, this one, the greedy one is, I think it's pretty cool, but also like the binary search solutions here. Anyway, I'll stop here, I guess. So you guys can pick whichever you want, and that's it. Okay, thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.